I'd like to welcome everybody to this next presentation in the series of Community of Practice webinars. Before I give my standard speech ahead of each of these webinars, I personally want to thank Pat Schroeder for helping me and helping us, over the past many years with standards, but especially with the community of practice. Without her help, we wouldn't be in the strong position we are. So the Risk-Informed Performance-Based Principles and Policy Committee, RP3C, of ANS has been putting on these events for the past 5 years. Presentations and recordings of the events are available to the public at the ANS website under the tab RP3C. There are now over 50 such recordings available. The purpose of these webinars is to offer practitioners of concepts and methods related to risk-informed and performance-based approaches, RIPB, a chance to share their knowledge and experience. I would expect that such practice is used for implementing nuclear technology and evaluating its safety and effectiveness. The purpose of RP3C is to help modernize ANS standards. The NEMA Act of 2019 associated modernization with application of RIPB approaches. Later, the idea of using RIPB to achieve effective regulation and oversight of nuclear technology became part of the ADVANCE Act in 2024, and now more recently, the executive orders issued, including 14300, have promoted the concepts of modernization. There is growing realization within the nuclear community that conventional, prescriptive, and deterministic approaches are not going to support increasing use of nuclear technology to play its rightful role for the benefit of society. Socializing alternative approaches could drive changes in industry and regulatory practices. ANS offers the COP files on its website to serve as a knowledge repository of the experience from a wide range of practitioners in the field. We hope that more people will use this knowledge base to speed up needed changes in the state of the art as well as the state of practice. These events are generally scheduled for the last Friday of the month. Today, we will hear from Mike Mankosa, and he will introduce the topic of his presentation and himself. Now, Mike, can you take over, please?
That's great. Thank you, Prasad. Thank you, Pat. So my name is Mike Mankosa. I'm a project engineer at FPoliSolutions, and I'm joined by Cesare Frepoli, who is the president of FPoliSolutions. We appreciate the opportunity to give our presentation today. So thank you to the RP3C community and everyone. Today we'll be discussing a digital framework we have called RISE, which is a risk-informed systems engineering tool, and it allows an analyst to develop a risk-informed safety case for current next-generation power plants. So just a brief acknowledgement, this work was performed under a DOE SBIR grant, so just we have the award numbers there. So RISE, this risk-informed system engineering tool, it was developed as we were reviewing the licensing modernization project and the NEI 1804 back a few years ago. And the way we envisioned it was to be sort of the framework for implementing the NEI 1804 approach for generating a risk-informed safety case and going through that development process. So the purpose of RISE is really to be a collaboration and productivity tool and to help automate as much of this process as possible. The tool is a web-based application that allows users to basically deploy it on their system and collaboratively work on developing this risk-informed safety case for either an advanced reactor or an existing LWR. So RISE is effectively a smart safety case builder for the design and licensing of nuclear reactors. So the current development status, we completed an SBIR phase 1, which is largely the content of this presentation, but we're showing the content more applied to an advanced reactor rather than an LWR. Because the SBIR topic was specific to developing risk-informed methods for application to LWRs. So even though the tool was originally developed for advanced reactors, we've really expanded it to be able to develop a risk-informed safety case for any technology. And in today's example, we'll be going through an entry we made for the modular high temperature gas reactor, the MHDGR design that was made by General Atomics back in the 80s. So here's sort of a high level code architecture layout of RISE. So RISE is built within FPoli app, which is our baseline application, which sort of hosts a database which connects all of our sub applications and also hosts the general username and login information and your sort of access panel to these apps. And within that, we have RISE built. And RISE is able to talk to the other applications within FPoli app, such as our simulation manager and data ontology tool, AUGMA. So the idea is that you can set up your risk-informed safety case and any simulations, including uncertainty analysis and simulation case management, and everything's hosted on the same centralized database. So users can very easily develop their safety case with very rigorous detailing of the history of the data trail. So it's a very transparent method for making sure all of your information is archived correctly and that files aren't erroneously shifted about. So we're going to walk through an example plant entry. Again, we're going to be showing an example of the standard modular HTGR. So when using RISE, it's a table-based application like you see on the screen here. These are all screenshots of the app itself. And so we begin by generating a plant entry and putting in some metadata for that plant. So you apply plant information, some more general information such as operating license, the start date of the reactor, the rated power, but you can also input information that can be iterated upon as part of the design, such as specific plant parameters like your power rating or flow rates or other applications or parameters of your SSCs. And those parameters can be used downstream to alter your simulations as well. Once you have your metadata entered, you can then go through and define your safety functions. So here's an example of the initial listing of the safety functions within the safety functions table. And when you open one of these items, you can then edit the metadata for that safety function. So the metadata includes information like associated events, whether this safety function is mitigating or preventative, and also associated SSCs that are linked to this safety function. You can also generate a hierarchy of your safety functions. So here you show up as a main or a derivative safety function. And ultimately, you can create a full hierarchy of safety functions, such as the one listed here. And then you can visualize it using the safety function visualization tool. And in this example, we have sort of the three typical primary safety functions: control of reactivity, confinement of radioactive material, and also removement of heat from the reactor. And then from there, we branch down into sub-safety functions. And this is fully customizable. The idea of the tool was, again, to be as technology inclusive as possible. So we make the framework for the engineer to expand as much as they want, or to keep things as brief as they would like for more simple analysis. So this is fully customizable. You can make your safety functions and their subsequent hierarchy as complex or simple as the user would desire. And then we have a very similar setup for defining the SSCs. So you first enter all your SSCs on a table, and you can edit their metadata. And then you can view the hierarchy of SSCs. So in the same kind of concept, you have sort of a high-level system, such as like your steam generator, and then you have subsystems or components such as the generator tubes or steam generator isolation equipment. And within the metadata, you can set preliminary safety or denotations for them, such as saying safety related or not. And then downstream of this, the idea is to actually test those assumptions and determine, based on the analysis following NEI 1804, whether these would be safety related SSCs or not. Next up, we go through and we can set the initiating events, event sequences, and event sequence families. So RISE is not intended to be a PRA tool in its own self. However, we do use a lot of the PRA information to perform some of the automated studies. So we're developing APIs to work with both Sapphire and CAFTA. And in this example, we had generated the PRA in Sapphire for the MHTGR, and then exported that information through the API and imported it into our RISE tool here. So all this information you see in the initiating events are from the original General Atomics reports from the 80s. It's all public information, but we all import that from the PRA model that we had made. So again, with these table-based entries, you generate your entry and then you alter the metadata. So if we look at an example here, for this particular initiating event, we can have multiple event sequences. So you set your event sequences, and then we group those event sequences into event sequence families. And again, it's very open-ended. You can generate as many or as few event sequences, event sequence families as you'd like. And within the event sequence family grouping, you can group them however you wish, and you just set certain distributions to be the more limiting ones, or certain event sequences to be the limiting event sequence. And then you can group as many as you like in that family, or you could also be more explicit and have each event sequence be its own family, so you have a one-to-one relationship. But again, all this information is automatically brought in through the API, so you don't have to go through and do it manually if you have an existing PRA. So with the definition of the event sequence families, you then relate both a consequence distribution and a frequency distribution. The frequency distribution information includes a mean value and a minimum 5th and 95th percentile uncertainty on your frequency. And that information from us is, again, coming in from Sapphire. And then you also can associate a dose consequence distribution. The dose consequences distributions can be made manually by hand or can be generated through our simulation manager. And then we can visualize it here. This particular example is just the evaluation of a single event sequence family. And we see that our uncertainty space is defined by 4 data points, which is the 5th and 95th percentile in both dose consequence and in the frequency space, giving you this kind of risk envelope. And we see that compared against here our NEI 1804 risk significance, and risk curve. And the event and fault trees can then be visualized. So again, this is all automatically imported from the PRA. And this particular example here is a control rod group withdrawal. And we have all of the downstream, the top events and our event sequences. The top events in RISE are denoted by a unique combination of safety function and SSC. So for our downstream automation, this is a requirement where within a given event tree, you have a unique combination of safety function and SSC. So for example, these first two top events, they share a common safety function, which is reactor trip. But the SSC in the first top event is control rods, and the second SSC is the reserve shutdown control equipment. And on the far end here, we have the event sequence name. We have the event sequence family name, and then we also have an end state. We don't have end states given for this particular event tree. However, you can define your end state as either core damage or no core damage, or you could be more specific and you can have an end state which is more of an encoded piece of information, such as is there leakage, is there core damage, is there a flow rate of a certain location, and that information can then be used downstream to help automate some of the core response and dose consequence response. And then for each top event, you can also import the fault tree information and then visualize that fault tree information. So here again, this is imported through the existing Sapphire tool, and then we just have the basic fault tree here with the gates. And again, RISE is not intended to actually solve fault trees, but it is using some of this information in the downstream analysis. So as I was discussing earlier, when we're defining our event sequence families, we have to input both frequency distributions and consequence distributions. And so they're both input as the complementary cumulative distribution functions, which you see on the right here. So this is an example of our distribution input for this particular frequency. And this came in through Sapphire, and we just have a very basic mean 5th and 95th percentile setting. But we're also in the process of developing the API for CAFTA under our current SBIR. And if you needed to, you don't have to use the API to import the things. You could always just manually generate these distributions. If you had them by hand, you can just open up this table and manually import these values. And the consequence distribution, very similar, also a CCDF. And the distribution doesn't need to be as simplistic as a mean 5th and 95th. That's just a minimum requirement. You can have your distribution be more detailed if you need. And under this current SBIR, we are working on developing the calculation of these dose values to work with your risk-informed simulation. So effectively, as you build your event sequences, you can then build those simulation of those event sequences using severe accident progression and radiological consequence and dose assessment tools. So we're looking at currently 3 different methods for doing this. One, we're going to be using a combination of RELAP 5.3D and RadTrad. Then we're also going to use Melcore and Max together. And then we can also use custom Python scripts if you have a more simplistic model that doesn't require as detailed of a severe accident progression. But the idea is that we're developing the framework for the user to use whichever tools that they're already planning on using for the severe accident progression and radiological consequence. We don't want to limit the user to a specific route. And like we saw with the event sequence family example, once you have this PRA information, it obviously goes on your frequency y-axis, and your severe accident progression and dose consequence assessment goes on your x-axis. And within RISE, you can set the specific metric to be whatever you'd like. You can have a 30-day TEDE, or you can have maybe more an operator dose if you want to look at that, or a smaller time span. So effectively, whichever metric you would like to analyze against is customizable in RISE. You just obviously need to generate your dose consequence analysis to match that. And so once all that information is imported into RISE and you have all your metadata set and you have your PRA information set, and once all of your dose consequence analyses are performed, or at least input to your distributions, you can then run the RISE analysis dashboard, which goes through the NEI 1804 sort of suggested analyses and calculates them for the user. So the first thing that's done is a very simple LBE classification. So in this example with the MHTGR, we started with 157 event sequences. Those were grouped into 82 event sequence families. And from there, we ended up with 60 LBEs, and those remaining 22, I believe, just fell out below the residual cutoff. With the remaining 60 LBEs, they're classified into AOO, DBE, or BDB, just purely based on their frequency of occurrence. And in some instances, given we're looking at the mean value of frequency plus the uncertainty, it's possible to span the border between a DB and BDB. So you can see that in this particular example, both are set to true. And then RISE will generate this FC chart on the dashboard. And this is sort of an expanded version of what we saw for the single event sequence family, but now we're showing all event sequence families. And again, these items are customizable, and on the RISE dashboard itself, it's interactive. You can actually click on your corners here and see the particular values and the actual metadata of that particular data point. But it shows you quickly at a glance, based on the input that you have on the upstream, do you have any event sequence family, or LBEs rather, that are passing through the risk significant curve or the risk cutoff line. And the customization that I was talking about earlier would propagate through here. So if you had a different metric, you can make a different table on the FC chart, and you can set these cutoff values to be whatever you wish. So if you want to use the NEI 1804 lines, you can. If you want to use a more DOE related approach, you can do that as well. The next part is the integrated risk metrics. So RISE will go through and calculate the integrated risk metrics by summing up the LBEs, the appropriate LBEs, and it will generate this summary table, and will show you whether or not it's acceptable based on whichever regulatory guidance you're following and the cutoff values that you enter for that guidance. And then RISE will go through and do some risk margin quantification, where we're looking at the mean frequency and the margin there, and the mean consequence and the margin there, and then the same thing for frequency and consequence in the 95th percentile and its margin. And we'll automatically generate some risk significance output based on the available margin or lack thereof. And next up, RISE does the safety function classification. And this is intended to be as automated as possible. So we will give a summary of the preventative safety functions and the mitigating safety functions, as well as we'll perform safety function studies to determine which safety functions would be considered required. And a lot of this particular automation is still under development, but we do have the automated safety function studies working currently. And the way that works is we look at a particular event sequence. So this has actually been done on an LBE basis, which is based on the event sequence families. So the event sequence family would look at whatever you select to be your limiting event sequence, and would then analyze that particular event sequence. So for this example, we're looking back at the control rod group withdrawal for the MHTGR and the second event sequence there. And the safety function being challenged is the reactor trip. So what the tool does is it takes the probability of failure, sets it to 1.0, and recalculates the frequency of this event occurring, and uses that as a new data point on the frequency axis. And then to determine what an equivalent dose consequence would be, it finds the sort of nearest neighbor approach for a similar event sequence that an existing dose consequence distribution exists for, and it uses that as a new dose consequence distribution. And then it will plot the new data point based on the elimination or the challenge rather of that safety function. And depending on where that data point lies, and this is for the mean only in this instance, it can be deemed to be a required safety function or not. And so again, for this example, we're looking at this control rug group withdrawal, and this is the initial risk envelope, and this is it just had a small small amount of uncertainty on the y-axis, which is why it looks like a flat line, but it's still a box. Just zoomed out a little bit. And this is our new location based on the elimination or challenge of the safety function for the mean value. So Roz will go through and march down the line for every event sequence family and perform this automated safety function, and then classify your safety functions accordingly. And then for the SSC classification, we're working on a similar approach where we effectively remove certain SSCs and then recalculate what your frequency and consequence would be based on the removal of that. And in this instance, it's a little bit more complicated than just looking at the event tree. So what we're considering doing here is considering that if you would want to challenge a specific SSC, the idea would be that this SSC is related to a specific basic event in your fault tree. And to eliminate that basic event, you could set that probability of failure equal to 1 again, but then you would have to recalculate your fault tree, which would require going through the full kind of cut set analysis and fault tree analysis. So we're looking at updating our APIs to automatically run either CAFTA or Sapphire to recalculate your fault tree and then recalculate your event sequences, and then pull that information back in to perform this particular SSC classification study. But for the time being, it's just showing as sort of a high-level summary of all the information for the SSC itself. And so ROS opportunities, we see opportunities obviously in the advanced reactor licensing. This is where we're aiming for. You can for generation of the RIPV safety case, providing transparency, scrutability, and collaboration, providing risk insights. And we're also looking into methods for maintaining and managing the safety case, including like in the world of TMASC, and then helping guide the analysts through complex workflows and automation of documentation. So again, it's intended to be a productivity tool that has really well organized data structures and a lot of transparency for easy review of your safety case. Within the world of LWRs, we're looking at expanding benefits from 10 CFR 5069 and also gaining any other risk insights or margin quantification for performing risk-informed type analysis when using a traditional LWR and comparing that to what the sort of more deterministic approaches would give you. And beyond that, promoting innovation and public acceptance, we're hoping it can be used to sort of enable deployment of highly enriched or high burnup or accident tolerant fuels, and also being used for siting and emergency planning zone management. And that's everything I have for the presentation. So now we'll have to open up to some questions.
Yeah, Mike, thanks for the presentation. So the first question that we've got in the chat is from Rahul. Can you go back to slide 17, please?
Yep.
And the question is about the classification of the event sequence families. And so Rahul is asking, can you please talk more about the algorithm behind classifying the event sequence families does the tool automate the classification process, or does the user have to do it manually?
Yeah, so this portion is all automated. It's really just based on the cutoff values you have for the AOs and DBEs and BDBEs, just purely in terms of frequency. So this is following the NE 1804 cutoffs for frequency. And again, excuse me, everything on the dashboard is fully automated. You basically click the check marks you like to analyze and hit run, and everything downstream is completely automated.
Great, thanks. I'll wait for any other questions or follow-ups.
Mike, this is Prasad Kadambi. I have a question. How do you address defense in depth in the model that you have developed?
That's a fair question. So with our current setup, defense in depth is really, we have effectively note taking for sort of defending your defense in depth approach. So if there's any questions beyond what you currently have, you can at least put some notes in the tool for discussion, but we don't have any direct defense in depth automation or application at this point.
But NEI 1804 does offer a model to, to at least simulate, isn't it? Defense in depth. Is that something that you could develop and add to your capabilities?
Yeah, it definitely is. In the current SBIR, we do have some of the scope set aside to perform some development there. But I'm sorry, in the current iteration of the tool, we don't have anything, but we are planning on addressing the defense in depth based on the NE 1804 approach.
Thank you.
Thank you.
Okay, so we have a question from Kevin about slide 8. So on slide 8, there was a tree leading down from the fundamental safety function, and he's curious about how that breakdown was approached, and if you have thoughts on how do you think it could be deemed comprehensive, the breakdown of the safety function, that is.
Yeah, so in this instance, the way when we went through this setup, it was more just for demonstration purposes of like the minimum viable product of the tool. So while we did think through this breakdown, it was more for demonstrative purposes than really a defendable a breakdown. So this is more example than anything.
Gotcha. No worries. Thanks.
Yep.
I did have one question in general based on kind of the shift that you've been talking about for the current SBIR. So you mentioned that the application was originally designed specifically for non-light water reactors, but now that you've been focused on use with light water reactor designs, I'm curious if you found any major differences or pinch points that would, be related to the methodology or the use of this specific tool between the different groups of designs.
I mean, the biggest holdup that we've seen is just the acceptance of risk-informed methods in the LWR community, and obviously there are some there, like the 10 or 5069 type approach, but with the prompt for the SBIR, it was really just to try and introduce the topic and try and effectively, get some momentum behind it. So our approach is to show the margin delta between the traditional deterministic, like Chapter 15 approach, and actually going through a full risk-informed analysis for a select couple of entries, and to show the margin that could be quantified following the NEA 1804 approach specifically. So while it's not necessarily something that could be accepted by the LWR community, it's at least saying, hey, this is a lot of margin here, and we compare that sort of to the BEPU methods from that were developed and were able to have a lot of margin gain.
Gotcha. Thanks. Yeah, that's good context. I'm not seeing any other questions in the chat. Oh, okay. Was the integration with Relap or the simple Python scripts only intended to calculate in-state consequences, or is there dynamic updating of risk states?
I'm sorry, could you repeat that?
So the integration, yeah, go ahead, Kevin.
So to ask it a different way, I was wondering if you could like input system, like current system parameters and get like a dynamic current risk state of the reactor to maybe inform like a decision-making tool.
Okay, so I'm not sure what you mean by that portion, but in terms of plant parameters, let me try and explain this a minute and see if it answers your question. The plant parameters can be input here and then used downstream in your simulations. So if you want to compare the state of a plant with certain parameters versus the risk profile of a plant with alternate parameters, basically copy the entire RISE hierarchy, change the plant parameters that you wish, and run the full thing again. And then the parameters will be used to execute the simulations. And you can see whatever alternative risk profile that can come up.
And is that integrated directly with Relap, or do you set up the Relap simulations separately, effectively?
Yeah, so the relap simulations are set up by the user. Our simulation manager, AugmaSim, uses Raven to generate sort of Monte Carlo simulations. So the user would have to build the relap model, but then once they kind of put that model into our platform, they can associate certain parameters to these plant parameters, and then Raven will alter those parameters, including uncertainty sampling.
Okay, gotcha. Thank you. Yes.
I'll give one last opportunity for
Well,
folks.
I'd like to ask a question, Brandon.
Yeah, go ahead.
Mike, you use the term safety case, and if I understood you right, this tool can be used to automate development of a safety case. Did I understand you correctly?
Yes.
So if you wanted to do that, how do you define a safety case?
So in this context, we're defining the safety case as really the NEI 1804 approach. So your risk profile based on your dose consequence simulations and PRA frequency.
Okay, thank you.
Nothing else from the chat. So, Steve Cron, if there was any questions that you had, then I can turn it over to you. And if not, then feel free to wrap us up here.
Sure. Thanks, Mike, for your presentation. Always valuable for the community to understand additional tools that it can use in making implementation of risk-informed methods easier and more readily available. And we appreciate you taking the time to come and brief us. So thank you very much. And to the rest of the community of practice, have a good weekend, folks.
Thank you all. I'll go ahead and end.